Hello everybody. We welcome you at Vector's and AdaCore's partner webinar today. I'm very proud to introduce you to our guest speaker, Robert Theis from AdaCore. And as always, we have my colleague Ingo Niklas from the technical department with us today. My name is Winfried Schröder and I will lead you through this webinar today. Let's take a look at our agenda for the next hour. We will have a very quick overview of Vector and the VectorCAST product family. This is followed by a presentation from Robert, who will show us how to meet the challenges of large and complex multi-language software projects. After that, Ingo will give a tool presentation where you can see how VectorCAST supports multi-language software projects. And at the end of this webinar, we will answer your questions. Please don't use the chat window. Please use the Q&A window to ask your questions instead. Only questions to all panelists can be answered. So, I'd like to start with a few facts about Vector. Vector today means 26 subsidiaries in 12 countries, and we are fast growing. Today we have more than 2,700 employees, which support more than 7,500 companies worldwide. As you can see on the timeline, the first release of VectorCAST was built in 1992. VectorCAST was designed as an embedded software testing solution for safety-critical applications in the avionics industries. The first version of VectorCAST supported Ada, which is still a popular programming language not only in the avionics industry. In the following years, VectorCAST supported other programming languages, operating systems, and compiler combinations. Today, VectorCAST is used in all safety-critical or business-critical industries. This is due to the testing requirements of the functional safety standards like ISO 26262 or DO 178 or IEC 62304, the IEC 61508 or various standards like Senelec and so on. VectorCAST is a testing solution for all phases of software testing, from low-level software testing to full system testing. Testing can be done natively on a PC or on a simulator or on the real target hardware as well, at all levels. VectorCAST products reside on the button and on the right side of the V model where testing takes place. On the left side, you see that VectorCAST integrates with other tools you probably have in your development environment, and it supports almost every embedded compiler. VectorCAST encourages a correct, complete, continuous approach of software testing. Code correctness and the full tested code is the basis for safety-critical software. As we all know, testing should be done early in the development process and as often as possible. VectorCAST supports it through automation, dashboards, and integration with other tools. It is always variable to see where you are with the test process and think about where you want to be in the future. Different organizations are at different levels across a wide spectrum. We are going to help you to reduce the time it takes to test, to increase the frequency of testing, to expand the responsibility of developing quality software within the organization, and to increase the amount of testing you have automated. VectorCAST has features that optimizes values in all these areas. So this was my very quick introduction in Vector's solution for software testing. I now pass the microphone and the desk to Robert from AdaCore.
Hi, this is Rob from AdaCore. So as soon as I'll show you some slides here and start to discuss some of the AdaCore tools that we have available. So everyone should see my screen?
Yes.
So for those not familiar with AdaCore, AdaCore is a company that specializes in developing compilers. And from our name, you may have deduced that we do support and maintain Ada compilers. So the company started as an open source solution for the Ada market, which was mandated by the U.S. Department of Defense back in the 90s. And from there, we've used that open source background to develop not only Ada compilers, but also C and C++ compilers and associated tools. So with those compilers, we develop and produce full tool chains, which include debuggers, full IDEs, all the tools you're used to in a compiler. We also develop tools which you can use to enhance your workflows, like static analysis tools to do security or safety analysis on your code. We can do coding standard checking, just in case you need to check your code against coding standards. You can do formal verification with the Spark subset of Ada. And you can do things like stack analysis. All of these tools are there to supplement and help you with your workflows as you're developing with the compilers. We also have a tool called QGen, which allows us to develop Ada and C code from Simulink and Stateflow models. And all of these tools can be used in certification environments like DO178 or Senelec EN50128. So the tool we're going to talk about today is specifically the GNAT Pro tool suite. This is a suite of tools that I mentioned earlier that kind of surround the compiler. So the compiler is the main feature here, but we also have the full tool chain. And for compiler targets, we have a lot of hardware and OS support. So anyone who is looking for a compiler, Ada C or C++ compiler for VxWorks or LinkSauce, or even a bare metal compiler, we have those available. And even those people who are using the bleeding edge hardware like RISC-V, we do have support for that. And of course, we have support for the native tools like Windows and Linux. Not only do we have the Ada support, but we also have the C and C++ support for a bunch of configurations here. There's a slightly better way to view this in this sort of form here. But as you can see, as new things develop, we are introducing C++ support for things like VxWorks. We already have these things for embedded Linux. So if you're putting Linux on an embedded ARM platform or in a PowerPC platform, we have Ada C and C++ available for that. And all of those tools available for the native stuff. Now, why would you get all of your compilers from a compiler vendor versus getting your C and C++ tools from your RTOS or from your operating system? So this is your typical development workflow when you're talking about a multi-language system. Typically, you'll have some Ada code, you'll have some C code, and you might have some C++ code. An example of this would be, let's say you're developing an Ada application on top of Linux, and you're only developing Ada. Well, that Ada runtime is actually calling C libraries from the Linux operating system, and that's how you get all of the tasking support and things like that. So in reality, even though you don't necessarily know, you are doing a multi-language application. And in many cases, you might actually say, hey, I have a C library that I want to bring into this application. You can do all of that, all of those languages in a single application. And the technology that makes that happen is the compiler backend. So the compiler front ends are going to be the specific language you want to develop in, C, Ada, or C++. All of those, the compiler front end takes all of those and passes that back to the GCC backend, and GCC produces the output binary. So this is very convenient because you can mix all of these things, and GCC is an open source technology. So it's nice that you have the ability to do this, but let's go back to the original question. What happens if I want to use my C and C++ compiler that's provided by my operating system? You can do that, but you might have a problem. And this would be the kind of the view of how that would work. Your Ada compiler would have a specific version of GCC. your C and C++ compiler would have a different version of GCC, being the C and C++ compilers from your operating system, the Ada compiler is from a vendor, let's say AdaCore. Now, you can do this tree. However, there might be some problems when you go to get to the link phase. So as I said earlier, C and C++ come from the OS. The Ada compiler comes from AdaCore. What happens when we get to the linker? Now what we see here on the bottom left is an example of what happens when you have a GCC mismatch. Now, what we're actually seeing here is GCC, well, the C++ ABI that GCC implements changes from version to version. So it's very possible that if you have different versions of GCC and you try to link them together, you are going to get errors like we see on the left here. Now, if you look at this error and you try to decode what that means, it's a little difficult. And in reality, you probably would have to ask a compiler expert to understand what these errors mean. Because if you look at this, it says undefined reference. It looks like a linking error, but it's pointing at a C++11 library here. So is it an issue with the C++ library? Is it an issue with the standard library? Is it an issue with the compiler? We don't know. So if you were to go back to this pattern where your GCC comes from a single vendor, being a compiler vendor, not from the RTOS, the compiler vendor, so AdaCore, can guarantee that that GCC version is the same for all three languages, so you won't get any weird linking problems. And if you do have any issues in the compilation or link or the development of your product with these three languages, and you have these three products from AdaCore, the AdaCore compiler experts are there to support you during your development. Any issues you have with the tool, any issues you have with the compiler, any questions you may have about your development process, the AdaCore experts are there to help you. What's nice about this is the VectorCAST tools can utilize these compilers. So your entire development chain now is you're developing with the AdaCore IDE, you're using the AdaCore compilers, you're using the AdaCore debuggers, you're using the VectorCAST testing tools, which is utilizing the AdaCore compilers. You have a single solution for a compiler that integrates in with your testing solution. So this is a nice combination. Some more benefits you may have from using the AdaCore compiler for C or C++ versus, let's say, the one that comes from your operating system is the ability to use vendor-specific pragmas, like this one. So the scalar storage order is a vendor-specific pragma that AdaCore implements. Those who are familiar with, let's say, the GNAT Ada compiler, so that's the AdaCore Ada compiler, may have seen this pragma in the Ada side, so the scalar storage order pragma. We can also apply this to C and C++. Now what this does is if you are porting your application from, let's say, PowerPC to ARM or PowerPC to x86, and this is coming up a lot more now that PowerPC is starting to go out of fashion, and actually in most cases it's being end of life. So a lot of applications, legacy applications, are now saying, well, now we have to support this new hardware which has a different endianness. So what they would have to do is go into the code and manually flip all of the byte orders to make sure that the record layouts or the struct layouts are correct. Now that's a lot of work that you have to put in. There's an easier way to go about that, and that's to use the scalar storage order attribute in C or C++ or the scalar storage order pragma in Ada. You can specify here exactly the endianness that you want this struct to be in, and the compiler will lay that out for you and will do all the runtime flips, bit and byte flips. There's another application where this is particularly useful outside of, let's say, porting from one architecture to another, and it's when you're on a little endian system and you have big endian network interfaces. So those who are familiar with 1553 or even Ethernet. That's a big endian interface. So you would want to actually specify any struct or record which is getting put out on those interfaces. You'll want to specify the scalar storage order on. And then instead of doing the manual flips in your code, the compiler can insert that code for you, ensuring that the code is correct. This will save you a lot of time and will save you a lot of debugging just in case someone accidentally set up the bit or byte flips incorrect. Using a similar compiler from Ada to C++ also is beneficial when you want to do exception propagation between the languages. In the demo that I'm going to show you shortly, we're actually going to see an example of this, where we're going to propagate an exception from Ada to C++ and then back to Ada. So it's kind of the inverse of what we're seeing here. Instead of C++ to Ada to C++, we're going to go Ada to C++ to Ada. The point being that if you keep the GCC version the same between Ada and C++, you can propagate exceptions across those boundaries. And that's pretty interesting because C++ can call Ada, Ada can call C++. You might get an error there. You'll want to inform that Ada can catch that, re-raise it, and then pass it back to your main. So this is very useful when you have a multi-language application. And this is another point where having different versions of GCC can be problematic. If you have GCC versions which are incompatible, this exception propagation will not work. And in many cases, if you get an exception which is thrown, let's say in the C++ end, so like where we see the throw X here, the program will just terminate rather than continuing on. So it's beneficial to it'll silently terminate, actually, and that's a problem because you're going to have to spend a lot of time debugging that problem. Whereas if you have a consistent GCC version on the back end, all of this is seamless. Now, in order to combine Ada and C, or Ada and C++, you do need to create an interface layer. And that interface layer in Ada will require a lot of pragma imports or pragma exports. That's the compiler pragma that says, hey, this is unreferenced in the Ada code, but the symbol needs to exist because it's going to be referenced or it's going to be implemented in C++, or vice versa. You might have something implemented in Ada and then the C++ side needs to see it. In that case, you'll use the keyword extern. What's nice is, what's hard about that is you have to start interfacing Ada types and Ada calling conventions with C and C++ types and calling conventions. This is an area where it's very easy to make mistakes. So it's more beneficial to use a tool which can automatically generate the binding. So here at the top, we have if we want to create a binding from C or C++ to Ada, an example of this would be if you have a C or C++ library and you want to utilize that from Ada, you can use the gcc-fdump Ada spec on the header files of that library. That will automatically generate Ada specs which map those calls into the Ada space. You can utilize them in Ada. You compile the C, you can compile the Ada, and the linker takes care of linking all the calls together. So this is very nice. This is how you would call C from Ada. Let's say you want to do the opposite, where you want to call Ada from C. This is where you use the -gnet CEG switch. In the example in the demo we're going to see in a few minutes, these switches were used to generate the bindings between the languages. Some more interesting tools that you have available with the GNAT Pro tool suite. So far we've only really discussed the compiler and what benefits there are from the compiler side. But from the external tools, you have a lot more support here. Let's say you want to understand a bit more about how many lines of code you have, or comment percentages, or you want to know something like cyclomatic complexity, which is very interesting to know because that tells you how hard it is to test something. Or you want to know entity coupling so that you can start to judge how hard it would be to refactor some code. This is a tool you can use called GNAT metrics, and that will compute all of these statistics for you and give you some output. So now you have some information, some statistical information about your code that you can use to judge, say, how much work it would be to do various tasks. You can also feed all this information into the GNAT check tool, which is a coding standard checker. And as part of the coding standard checker, you can check things like the statistics I just mentioned. So you can, let's say, cap the cyclomatic complexity at some value to say this is the max cyclomatic complexity my application should have. And then when you run the coding standard checker on your tool, on your code, and your code, let's say, has a higher cyclomatic complexity than the max, the tool will tell you, hey, this piece of code here needs to get refactored into something simpler. You can also put in style-related rules, so like pretty printing, you know, how the code should look, or what features that you're using. So let's say you don't want to allow tasking, or you don't want to allow object orientation, or you want to guarantee that you're using portable pragmas and not vendor-specific pragmas. You can do that with the coding standard checker. This tool is particularly useful to use before a peer review, because as part of the peer review process, you can show the output of this tool to say, hey, you don't need to look through every line of my code to verify that it looks correct and has the right features. The coding standard checker did that for me. We also have a tool called GNAT Stack, which can predict the maximum memory requirements for an application. This is if you're doing a bare metal application. What's nice about this is in most bare metal configurations, typically you have limited RAM. So you want to verify that you're not going to blow your stack. So you can use the GNAT Stack tool to calculate predict the max stack usage for Ada and C applications. There's also a tool called Spark Discovery. This is a light version of our Spark Pro tool. Now, Spark is a subset of the Ada language, which is fit for formal analysis, formal proof analysis. So what that means is we remove anything from Ada which has undefined behavior. And that's really only pointers. Pointer aliasing is the only thing that's undefined in the language. That's undefined in all languages, actually. So if you remove pointers from or access types from the Ada application, you're now within the Spark subset. Now you can use advanced formal proof and static analysis techniques to verify that your code is absent of runtime errors. This is a supplement to your testing strategy. In most cases, you're going to be doing black box testing anyway. This is a way to minimize how much time you spend debugging applications, because you can verify statically that your code follows your requirements. This is kind of a nice tool, and again, it does require that you subset the Ada language. So the Spark Discovery tool allows you to do some of this. It allows you to check to make sure you're within the Spark subset, and allows you to do basic data and control flow analysis. So it looks for things like dead code, and variables that are used before they're initialized. It looks for things like tests that are always true or false, meaning if you have an if condition and that if condition will never hit the else, let's say. It'll look for things like never-ending loops that will make sure that the loop exit condition can be met. These are all things that the Spark Discovery tool can do to help you make sure that your code is correct. All of these tools, so the compiler, the debugger, the linker, all of the GNAT metrics, check, stack, and the Spark Discovery here, that can all be used from GPS, or the GNAT Programming Studio. This is the AdaCore IDE. or integrated development environment. All of our tools are command line, meaning you can run them from the command line. This is particularly useful when you're setting up a continuous integration environment, or if you have developers who are more comfortable developing on the command line. We do have a lot of AdaCore employees who are developing pieces of the compiler who are still using Vim and Emacs. So if developers are comfortable with those languages, or those development environments, you want to make sure that they have those tools from the command line. But for those people who are more comfortable with a graphical interface, that's where the GNAT Programming Studio comes in. And that's what we're going to see the demo on in a few minutes, where all of these tools are integrated into a nice IDE. So this is nice because you still have the ability to call all of these tools from the command line in all of your build scripts, and you have the ability for developers to develop their applications in a comfortable graphical user interface environment. So now we're going to go see a demo. We're going to show the GPS tool. Everyone should be able to see the GPS development environment now on my screen. So this is what we're looking at here is a project called SDC, or Simple Desktop Calculator. It's for those familiar with an RPN calculator, or reverse Polish notation calculator. It's a different type of calculator that utilizes a stack data structure. So if we look at the bottom here, we can type, normally if we wanted to do math, we would do something like that, to do 2 plus 2. And the reason we write it like this is because that's how we speak. We say 2, the operator, and then the number, so number, operator, number. But computers are actually a little bit better at doing something like that. So 2, 2, and an operator. What that allows the computer to do is take the first number, push it onto a stack, take the second number, push it onto a stack, and then get the operator, pop the second number off the stack into the operator, pop the first number off the stack into the operator, and then do the operation. So if I were to do 2 plus 2, 2 plus, I would get an output of 4. What's nice about this is I can also do something like this. And then that'll do the math for me. So what we're looking at here is a stack, some string parsing, and an I/O interface. So the I/O interface, the user interface part, what we're seeing down here in the console, is done from Ada. So we have a little bit of an Ada application here, which brings in a string from the command line, calls some code, and calls a subprogram here, and then outputs the result. If you notice here, there's a fairly large exception handler here. This is where most of all the exceptions are going to be handled. In the other parts of this program, the exceptions are just going to propagate all the way to this main handler. So if we want to look at what we're calling here, we're going to parse the input tokens, the characters here, using a parse tokens function. If you see here, we have an import and a convention. This is a file that was automatically generated by the binding generator. So the binding generator said, oh, hey, I want to create a Ada binding for this C++ function. So I'm going to generate the correct types and put in the correct aspects here to say that this is pragma export, pragma convention is C++, and the best part about this is it automatically calculates the mangled C++ symbol name. So when the linker comes by, it knows what to look for in the link. If you don't use the automatic binding generator, you'll have to guess this name, which is very difficult. You can see we also did the opposite. We created We created a C++ header from an Ada. We created an Ada spec from a C++ container, or C++ header. What was interesting about that was the implementation is in Ada. So I wrote the Ada side, generated the C++ header, and then recreated the Ada spec, and that automatically generated name mangling. And again, the best part about this, using the automatic binding generator, is the name mangling calculations. So what I do here in the C++ code is we do a bit of string parsing. This is the parse tokens function. So we get a string from the user. We pass that into the C++ code. The C++ code does some string parsing. And of course, C++ is great at string parsing. We have all these wonderful standard library operations. We can do things like this, where we can just put a string into a string stream and then parse it on white space. And then once we do that, we're going to push each string. So we get, it parses the string on white space. So now we have a list of strings inside the string stream. And then each string in the string stream, we're going to push onto a stack. Now that stack is actually in Ada. So as you can see here, we have push and pop operations on a stack. If you notice, in the push operation here, we can see that there's a raise overflow. So just in case we push too many values onto the stack, because this stack has a maximum size, this exception will be thrown. That exception will propagate into this code. Here's where we're calling push. As you can see, there's no exception handler here. We do have some throws, but we have no exception handler. So that will propagate back out to the main, which was here, and it'll be caught right here. So we're actually going to show that. So what I'll do is I'll type in, we'll actually find our maximum stack size. Our maximum stack size is 10 elements. So I'm going to go in and say 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That would be max. Let's put in 11. Now, what just happened there? Ada threw an exception. It was propagated to C++. C++ propagated that back to Ada, and that was caught right here. So using the AdaCore C++ and Ada compilers allows us to do this exception propagation completely seamlessly. There was no extra machinery I had to do to get this to work. I just wrote throws and raises and exception handlers just like I would with a normal application. So this is fairly nice. All of these bindings were automatically generated. All of the exception propagation just works out of the box. And in order to actually build this application, I'm going to kill the process quickly, and then we can just clean and build. So, it's very easy. I can just click around. It'll build and link my application together. You can see I have some warnings here. These are some interface warnings between Ada and C. The compiler is just telling me that maybe there might be some type mismatches. This is nice to know. The compiler is smart enough to know that Ada types and C and C++ types are different. So if you look at, let's see, an Ada type, an Ada Boolean is actually just an enumeration. And the size of that is determined by the compiler, whereas in C and C++, the Booleans are different. They're laid out different. Typically, they're an 8-bit character. So what the compiler is telling me here is that this Boolean type and this type here, this bool, are different. That's not a problem for this application, so I can safely ignore these warnings. But it's nice that it tells me these warnings just to say, hey, did you check this? And you can see we went through the link phase, so our application is linked together. I can run that application, and we're back to our original application here. I can also do things like I've only used plus, but I can do things like this. If you notice, I actually put in a bad string because I didn't put a space here. So that was actually, this is actually a C++ application, exception being thrown to Ada and Ada catching it. So if I were to do something like this, because I accidentally forgot that this is an RPN calculator versus a regular calculator, the string parsing, which happens with a regex, right in where is that? Sorry, right here. Yes, here's the validate input. If this throws an exception, then that's being caught by the Ada side. I can do, so let me do what I was actually going to do. There's a subtraction. If I were to do something like, there's a division, but if you notice that was a divide by 0. So that's 3 divided by 0. That gave me an exception which was handled, wasn't handled actually. So that's a constraint error. So all of this gets, all of this is nice because all of the exceptions are just handled by the language that you wrote them in. You also have access to the other tools I mentioned earlier. So I can compute metrics about this application. If I were to go in and compute metrics, I can run a coding standard check against this this project. I can generate documentation from this project. So the Gnat doc tool is a tool which will read all of the specifications of your code and then automatically generate HTML documentation, kind of like Doxygen or JavaDoc. So if you're familiar with those tools, we have a tool that's very similar and allows you to do that with Ada. We can also do integrated debugging. So I just clicked on the debugging symbol. That starts a GDB session. So I can do things like, let's break at this line, and I can hit run. So we're waiting on some input. I'm going to put in some input into the and I'm looking for the, oh, yep, there we go, sorry. Continue. So now we're running. And I can pause, figure out where we are. We have the ability to do, we can examine memory. We can look at the assembly. So we have the ability to do all of that. And that's actually automating GDB. So you can see at the bottom here, I can look at variables. So if I were to do that, that gives me the string here. So that's what's inside that variable. So I can either do all of this from the GUI or I have the GDB console at the bottom here. That's kind of nice because that's all integrated into one environment. Now you might notice there's a button here called Start VectorCAST. This isn't a standard button inside GPS. However, so this is a custom button that I've put in here. What you can do within GPS is you can script, you can put in your own plugins and your own buttons, your own menu items. And what that allows you to do is to integrate anything else in your workflow that you want to integrate into your single IDE. All of this plugin is done, all these plugins are done in GPS, so, or in Python, sorry. So GPS has a Python interpreter built in. So when it starts up, it's going to look at all the plugins and load all the plugins. So in this case, I have a plugin here which is called Start VectorCAST, which will run the VectorCAST tools. I'll actually pass this over back to the VectorCAST side so they can show some of their tools at this point.
Okay, thank you very much, Rob. Then I will take over and show how we can use VectorCAST in large and complex multi-language environments. So for this webinar, I got the project from Rob, and together with the button, and behind the button lies a batch file, and I filled this batch file with the start to the VectorCAST project. So what I prepared was a testing project, and I configured VectorCAST to test two of the units, two of the files that are part of the project. One of them is the Ada file that has the stack code in it, and one of it is the token file, C++ file with the logic of the calculator. So what we see here is a test project. The advantage of it is we have all testing activities, all dynamic testing activities like unit tests, software integration tests, or code coverage from system level test, we can integrate into one project. We can show, for example, coverage of one file that is part of different test environments, maybe part of a unit test environment and also part of a system test environment where you measure coverage. We can integrate this coverage and show it on one file overall testing activities. Also, what we have here is the compiler switches, where you can configure what's the compiler that is used, what are the compile defines, what are the include paths, and then when you right-click under this node of the compiler and you create an additional unit test environment, then this unit test environment will inherit the settings from the upper nodes. So not everyone in the project needs to care about those settings. Many people in large teams will not need to bother about compiler settings. They just want to create test environments for their specific parts, for their packages. And so it's a nice thing to have a prepared project that has everything ready to go. Also in multi-language or big, large project, it's always good to have some reporting, some overall reporting, not only coverage, but also, for example, cyclomatic complexity. We already spoke about it. With VectorCAST, we can, for example, show all the subprograms, the functions that are involved, all the files that are under test. We do also show the cyclomatic complexity because we analyze the code, so we also know how complex the code is. And then you can sort, for example, by name, or you can sort by cyclomatic complexity and see what are the functions, what are the subprograms, what are the procedures with the highest cyclomatic complexity. Then look at the code coverage, for example, how much statement or branch coverage do we have, and then focus your testing activities on these parts of the code. So we did many webinars in the past, and most of them were about the languages C or C++. So today I thought let's focus on Ada, and let's have a look at the Ada unit test environment. So I prepared one already for the stack. So let me just open this one. What we see on the left is the name of the unit test environment. We see the name of the unit under test, which is in this case the Ada package stack container, and we see the functions or procedures that are implemented inside this stack container. So if we want to create unit test environments on or unit tests on a stack, then one thing that we want to test is we want to push data to the stack, and we also want to pop data from the stack. So let's start with a little bit of deep dive into unit testing. We create a test case on the push procedure. And if we look at the source code of this push, then you see this is all Ada. We have a input-output parameter of type stack, and there is an element that should be put to the stack or pushed to the stack. So in out, for those who are not so familiar with Ada, means it's a call by reference in C, and the element is a pure input parameter. So we want to put something to the stack, and the stack itself is not a global variable, it's a parameter passed to the function or passed to the procedure. So here in the test case, we see the function that we want to call or that we want to test. This is the parameter self with the stack itself. The stack has a pointer to the last pushed element, and it also has a table. And the table is a stack container, an array of integers. And we can show as many elements as we like in VectorCAST, for example, the elements from 1 to 3. And then we want to test the function, and we want to add, let's say, element number 1. And we would expect that it appears in tab number 1. So we expect that after the test case, we will have, not in 3, but in 1, we will have element number 1 here. So when we run this test case, it should work fine. We see it passes. And now we can create additional test cases and, for example, add the elements 2 and 3. So let's quickly just do that. we add value 2, and we expect 1 and 2. And let's just duplicate this test case. And then we add element number 3, and we check that it is at the stack. Now, when we run these 3 test cases, we will see something surprising, which is we have 1 passing test case, which is nice. And when we look at what we see, we call the push function, and we see that there is nothing at the stack when we start. We push element number 1, and then when we return from the push function, we have 1 stack container element, and we have the actual value 1, which is what we expected. But when we call push the second time, we see that the stack element array is empty. There are no elements stored, which is not what we had expected. And why is that? That is because VectorCAST creates for each test case is an individual task run. That means each test case is independent of all the other task runs. And you can see this if you look at the jobs window, for example. When we run these 3 test cases, these are 3 calls to the executable, 3 independent calls to the executable. Now we can change that by adding a compound test case, and the compound test case allows you to run test case one after the other in 1 task run. So we just drag and drop these 3 test cases over to the compound. And now when we run the compound, we see it's just 1 executable that's executed. And we see that the result is pass, because after the first call, the element is there. And then when we start the second call, the container has the elements that we pushed in the previous test cases. Now, if we want to add a pop test case, we want to get something from the stack that we just filled. Let's say we call pop inside the compound. That means the first time we call it, we would expect that we get value number 3. So if we add this test case to the compound, to the end of the compound, then we see again something surprising, which is the test case fails. And why is that? We see that we get an unhandled exception. We see that when pop is called, we have a stack container underflow. And the reason for that is because the functions or the procedures get the stack as a parameter. VectorCAST creates global objects, global variables for those parameters. And of course, each function gets its own global variable. So when we call push, we store things to the global variable that VectorCAST builds for the self parameter of procedure push. But then we call pop with a different global variable. So if we want to test the pop on the same stack, then what we need to do is we need to assign the global object that we use in push and copy it over to the test case in pop. And we can copy this global object or the user code tag that you can use to access this global variable by right-clicking and copy. And then we go to the pop test case and we use user code to store the stack from the push test cases to the pop test case. So when we do this, this means that when we run the test case, during runtime, we assign the stack from push to pop. And that means this needs to be compiled. So when we run this test case, now as inside the compound, you will see that we call the GNAT tool chain to compile the code, because now since we want to run the code when the test case is executed, it needs to be compiled, it needs to be linked, and therefore it takes a little time to build the unit test executable. And we see that we use the GNAT compile to do that. And then the test case passes, because now when we call pop, we have the stack container from the push test cases. Now, let's look at the code coverage. VectorCAST can measure code coverage on the source code. We measure, for example, statement and branch coverage in this case, but we can also measure higher levels of code coverage like MCDC, for example. And you see lines that are marked in green for lines that are covered. That means they are executed, and when you hover over the line, you also see which test case executed the line. Lines that are red were not executed, and then lines which are yellow or orange are partly executed. Now, we very often get the question, what do we do if we cannot provide 100% code coverage? We can only get coverage from, let's say, 90% of code, and there are 10% of lines or 5% lines are uncoverable. What you can do then is you can justify those lines by comments, by writing additional comments. Some people do this outside of their coverage tool that they use to measure coverage from execution, but we can do this inside of VectorCAST. Just right-click the unit under test where you want to add additional coverage. We then have a checkbox left to the uncovered lines. For example, in POP, we can tick these two checkboxes. You see that they appear in a different color, which is blue. And there is an additional indicator, coverage indicator, a capital A. That means we have covered by analysis, so we can write our justification, whatever that may be, why this code is important and why we were not able to execute it during runtime. And then when we save this coverage and we look at the coverage report, then you see those lines in blue, like here, with the additional coverage indicator A for covered by analysis. And in the metrics at the end, we show 100% coverage on the subprogram, on the procedure, on the function, which is what the auditor or the certification authority wants to see. And when you look at the details, then you see how many percentage of the coverage came from execution and how many percentage came from covered by analysis. Also, what we can do is we can do functional testing, which is also very important in, for example, in safety critical environments. And when you do functional tests, you usually want to have requirements. So in VectorCAST, we allow you to import requirements from your requirements management system. And for this purpose, we implemented a requirements gateway. And the requirements gateway works in a way that we access a database, and you can configure the database folder on the Builder tab. There is the location of the database. So if you have a large, complex, multi-language project, then you will most likely have many files that verify different requirements, maybe even in different written in different languages. So if every language or every test environment refers to the same database, to the same requirements gateway database, then all of them can do harmonized reporting because they all use the same imported requirements. The importing itself depends on the requirements gateway that you're using. Here is an example of the requirements management systems that we support out of the box, and we already ship VectorCAST with Python scripts that realize the access to those requirements management systems. As an example, I imported some requirements from a CSV file, and when you look at the View tab, then you see the requirements that we imported. They have an ID, they have a title, and when you hover over one of them, then you see the description of the requirement. So we can, for example, link requirements then to test cases. And for example, if we wanted to check, so if there were a requirement saying if we try to get data from the stack and there's no stack, no element available, then we would accept an exception, and the exception should be stack underflow. So this can be a requirement, and we can link it to a test case just by opening the requirements window and then double-clicking the requirements that describe this functionality, and then in the test case, for example, for this purpose with the exception, we can say we expect that in this case we will see a raised exception saying we have a stack container underflow. If we expect to, if we call pop without pushing data first. So like this, you can also verify or write unit test cases on exception handling, for example. So back to the project, when we go out of this unit test environment, then we see how VectorCAST stores the test case data, which is also very important if you work with large teams in teams that are spread over the world. Then it is important to have the test case data, to have the test project stored in version control, stored in any kind of source code management. And if you need to merge things, if you need to merge test cases, if you want to reuse them maybe in different variants, then it's important to have the test cases written in a understandable way. And this is how VectorCAST stores test cases. We have things in a human readable version. This is test.value, those are input values, and then we have test.expected, that's an expected value. And this is how we store the data. It can be stored to version control in ASCII format. Yes, in a large project, it's also important to reduce testing times. So that's why we implemented the change-based testing. So if you want to rebuild everything, you can do the build full on top level. This, of course, also works from the command line interface. But most people or most developers want to have instant feedback on their code change. Did I introduce any additional bugs? Did I reduce code coverage with my additional code that I created? So the incremental rebuild is what you usually do to see whether you, as a developer, created a bug in the source code. So you see that when we do the incremental rebuild, we look at the source code. Did anything change? And if no source code changed, then we don't need to rebuild anything. And also we look at any code changes, if there were any, or unexecuted test cases, and then run the unexecuted test cases or run those test cases that were affected by a source code change. By the way, we can do this not only in unit or integration level testing, we also can do this for system level test cases. Finally, reporting. We have a dashboard, and the dashboard also works in large projects, in multi-language projects. The dashboard just started over here, so let's move it over to the presented screen. Okay, we only have these two files, but we show the overall reporting on the project for these two files. This presentation is hierarchical. That means we can dive deeper into the folder, the sub-programs, deeper into the units under test, and then see how well the coverage is. On the left side, we see code coverage versus code size. On the right side, you see code coverage versus complexity. Green means we have a good code coverage. Red means we have a bad code coverage. So we get an instant overview over what kind of coverage do we have on our code. Where are the areas where we should spend some additional testing activities? Maybe the more complex ones should be tested first. And also we see what are the functions with the highest complexity in the area where we are looking at, or what are the files with the highest complexity. So I hope that helped a little bit in getting an overview of how to test large projects, multi-language projects. Yeah, so we are ready for question and answers. Feel free to add additional questions into the Q&A panel. Who continues? Winnie, back to you.
Yes, thank you, Ingo and Robert, for your presentations. As Ingo said, we are now at the Q&A session. If I have a look on the questions, I see that there are already some questions for you, Robert. Can you please read and answer them?
Sure, yes. So first question I have here is, can VectorCAST tools utilize the AdaCore compilers? So the answer to that is yes. So in this case, the VectorCAST testing tools can utilize the AdaCore tools to compile the application. This is particularly useful because you're going to want to run the tests with the same compiler as you're going to be shipping the application, especially if you're in a certification context. So it's very beneficial that the VectorCAST tools can utilize the AdaCore compilers. I have another question here. Does AdaCore have any tools for static analysis or security analysis for Ada? The answer is yes. So we are seeing a significant amount of the industry start to focus on the security of their applications, especially in avionics, and things that are safety critical are now also becoming security critical. So AdaCore's tool for this is called CodePeer. This is an advanced static analysis tool that allows developers to detect potential runtime errors that can be exploited in the cybersecurity context. Here's an example. If anyone is familiar with the Heartbleed virus, that Heartbleed bug, that wasn't a virus, that was found a few years ago, the premise to that was it was actually a buffer overflow that occurred in some C code. If that were Ada code, that could have been detected before deployment using the CodePeer tools. The CodePeer tool can look to say, hey, there's a potential buffer overflow here. You should probably check that. A lot of the CodePeer findings can be mapped to CWE numbers, so common weakness enumerations. This is particularly useful when you need to start to communicate to security professionals about the status of your code. You know, if you explain your code to a security professional who isn't familiar with the language you're developing in or isn't familiar with your application, it might be difficult to describe to them what, let's say, an array index check is, which is the equivalent of an Ada buffer overflow. Where if you were to say CWE 120, that's a buffer overflow, an array index check. It's all of that language is mapped to that enumeration. The CWE numbers, this is common because there's a security company called MITRE, which has come up with this enumeration list. So it's sort of becoming a standard in communicating security needs, and CodePeer can do all those mappings. And one more question we have here for AdaCore is, are there any resources for new developers trying to learn Ada? It's a good question because there is. We just launched a new learning platform called learn.adacore.com, which is an interactive learning website. So there's an intro to Ada and an intro to Spark course on there where you can view the course and actually run sample code right in the browser. This is very useful if you have new developers coming into a project and they don't know Ada. In most universities, they're teaching C, C++, Java in school, so you might have a little bit of an familiarity with Ada with new developers. You point them to that website, and within a few days, they should be up and running and proficient at Ada. I think that's it for the AdaCore questions.
Yes, thank you, Rob. Ingo, same question to you. Do you have got any questions you can answer?
Yes, whereas Rob already answered the VectorCAST question regarding the compiler and whether we can use the AdaCore compiler, and perfectly well. So yes, of course, we can use the AdaCore compiler. By the way, VectorCAST itself is a multi-language application. I know that parts of it are implemented in Ada, in C and in C++, and we have a very long relationship with AdaCore. I'm not 100% sure, but I think we even use the AdaCore compiler to build VectorCAST, but that's a different story, so don't yeah, not a fixed statement. Not definitely sure. I'm not part of the development. In general, it's of course important, especially in safety critical environments, as you said, Rob, to run the dynamic test cases using the same compiler that is used to build the project. Because otherwise, what's the worth of what's the value of a functional test case if you test it using a different compiler? So that's kind of useless. Here's a question on the reports, why they look different in my VectorCAST. Is this because of Ada? So the execution report that I showed and also the aggregate coverage report that I showed, they look maybe different because of the version that I'm using. I'm using VectorCAST version 2019, and now we have HTML style sheets that we are using, so we did some improvement on the reporting. That's why, and not because I used the language Ada. So it's in C and C++ the same. One question on huge projects: how can tools help in automatically creating the test environment? Well, we have a tool called VC Shell, a command line tool that allows you that is able to log all commands that are executed while building a project. And when you build your project, all files are compiled, and since we log all compile commands, we can automatically derive the compiler settings from these compile commands, and we can also automatically create unit test environments and even create a test project on top of that. We could even automatically create test cases that could provide some code coverage, but this is probably too much to just explain. So if you're interested in features like this, then please get in touch with us with vector.com or whatever. And finally, there's a question whether we can write requirements in VectorCAST. No, it's not possible to write requirements. We have a test case notes section. You can write notes to your test cases or to each test case individually. So this is kind of a test specification for a test case. And we should be able to also export the tests at the test case notes section into the requirement management tool. And this is usually helpful in certification because it's kind of a test specification. But VectorCAST itself is not a tool to write requirements, but we can import requirements from different other tools. So far from my side, I don't see any additional questions. So yeah, back to you, Winnie.
Yes, thank you, Ingo. We are a little bit late and have passed our time. So if you have any questions, then please send it via email to us. We have to come to the end of this webinar now. I'd like to thank Robert and Ingo for your presentations and demos. I'd like to thank all attendees for your interest and the time you spent with us today. We hope you enjoyed this webinar and we can welcome you again at one of our next events. Goodbye.